good morning, everybody. Yeah, my name's John. I'm with Sporlan, and whenever I'm talking to a group, I never know where everybody's at. So, like Ruben was just saying, I mean, he's brand new to CO2. Some of you guys probably have a lot more experience with CO2 than me, and you all have a lot more field experience because I'm not in the field. I represent Sporlan, and Sporlan is owned by Parker Hannifin. Parker Hannifin also has under the Sporlan umbrella, we have the RS group, so A8, A9 valves. We've also got the all the industrial products from Refrigerating Specialties, and we also have microthermo. So if you haven't seen that presentation, we've also got that being showcased this week. Some of our team are presenting the microthermo product. So I have this really amazing skill of getting eyelashes in my eye. I don't know, I seem to get them in my eye at a high frequency, and I just got one just a minute ago, and I was like, oh man, I'm gonna be screwed here. So we'll see how it goes. Hopefully it'll stay out of my way. So my goal is to, my goal is for you guys all to get something out of this, and it's kind of an introductory presentation. I'm going to go through some of the stuff that we've got, that Sporlan's got, and for starters, what I'm going to do is I'm just going to give a little bit of an introduction to refrigeration. I'm going to try to lay something of a foundation to build on as we move forward. That will include just a quick look at just a standard multiplex rack system, and then secondary glycol and the attempts that were made to utilize that technology. And then we'll move into CO2 systems, some of our components, and then I'll talk briefly about our S3C Case Controller. So here we go. Let's go back to something at the beginning. So refrigeration, cold is something that people put a high value on. We depend on it. And as we saw through COVID, refrigeration is an essential, it's an essential industry. So back in the day, it took a whole lot of work to get the job done, and that included harvesting ice from ponds and lakes. They'd take that and they'd stick it in like facilities or quarries, maybe like caves, where they would pack it with sawdust and straw to preserve it, and then they could pull it out later in the year when it was hot. And a lot of times that would be taken to domestic locations or establishments, stores and whatnot. And this is just kind of a fun little picture where, you know, you take that ice and you put it in the ice box. So today we have domestic mechanical refrigeration in every building in America pretty much. But we still call them ice boxes a lot of times. So that's where that comes from. So speaking about ice, it's worth noting that it takes a ton of ice to get 1,200 BTUs per hour of cooling. It takes a little bit larger than a 3-foot cube of ice. And what that'll get you through empirical analysis, they've been able to determine that equals, over the course of a day, as that ice is dissipating the energy that it has, there's 288,000 BTUs in a day. Do the math, that calculates to 12,000 BTUs in an hour. So that's a ton of refrigeration. And so, you know, to get that done back in the old days, again, a lot of hard work. Nowadays, 1,200 BTUs, pretty easy. You can get that down at the local hardware store and stick it in your window if you wanted to. So it's nice, it's a good thing. Grocery stores are another good thing. We've got, as Jason said, you know, 50,000 plus existing stores across North America, and we're adding, you know, anywhere from 1,000 to 2,000 stores a year to keep up with the demand. Lots and lots of dollars in product, and this is all a huge opportunity. It's an opportunity for us to sell products. It's an opportunity for service technicians to service products. It's an opportunity for manufacturers to innovate and come up with new technologies like CO2, refrigeration systems, and on and on. our customers, our end customers are the supermarkets. I'm not endorsing any supermarket in particular, but that's who's using our products. That's who the contractors are working for as well. And there's a lot of change going on with supermarkets. A lot of markets, one market buying out another market or integrating with other companies. And then our other customer is the OEM manufacturers. So a lot of these guys are buying our products and integrating them. And there's a lot of changes going on with the manufacturers as well. A lot of conglomerating and one company getting absorbed by another. So at the lowest level, you've got everybody that goes down to the store and buys that product, and that's where the refrigeration is required, and it's changing. That's changing as well because we have a lot more of these things going on. We've got online ordering. Probably most of us have done that at this point. Curbside delivery, home delivery, in-home delivery, in your refrigerator. Anybody doing that? Anybody getting product delivered to their refrigerator? Okay, I had a couple guys in my last presentation who they do. Yeah, they get they order it online and it shows up in their refrigerator. So pretty crazy. Grab and go. I mean, that's some new technology. Go to the store, grab it and go. You don't have to go through the checkout lines. We've got in-store restaurants and bars and some of these larger supermarkets. A lot of C-stores going on. A lot of smaller point of in conjunction with like the online and the home delivery. You've got other remote warehouses, cold warehouses that are being put in, and on and on. So the changes are everywhere. So changes on the refrigerant side, there's a lot of regulations that continue to roll out from the government, EPA, DOE, and so that's moving us into different refrigerants, lower GWP refrigerants. Stores are having to change their platforms. There's a lot more integration of electronics, and the labor force is changing. The labor force, a lot of the labor force is getting old and retiring, or a lot of that going on, and so you got a lot of new guys coming in, and there's a lot of stuff. There's a lot of knowledge that we need, and we need to try to grab that as quick as we can before it's gone. But there's a lot of new knowledge that we're acquiring to get the job done today that wasn't used yesterday. Here's another instance or example of change. Annual walk-in energy factor, AWEF. So this is for walk-in coolers, freezers, anything 3,000 square foot or lower. The Department of Energy has mandated that you've got to satisfy their energy requirements, whether it's a new install or a retrofit. And a lot of times that affects the selection of the expansion device. And it's something of like a SEER rating for walk-in refrigeration and freezers. So I'm not going to go into more on that, but worth noting. And this is just kind of just talking about, where are we going? What's it going to look like in the next 5, 10, 15 years? Well, 15 years is the life of a lot of these systems. It can go, a refrigeration system can go a lot longer than that. A supermarket can go a lot longer than that. But at 15 years, a lot of times they're being retrofitted or replaced. So in that time, I think we're going to see a lot of change. We're constantly needing more efficient systems, cleaner systems, no leaks, and again, that's leading to electronics and low GWP refrigerants. There are some talks going on today about propane. I'm not going to talk about propane because that's not what I'm going to talk about. Sporlan is propane ready. We've got components for propane, no problem. From filter dryers to expansion devices, all the way down to flame-free connection options for connecting your pipes. But we're going to talk more about CO2 in this session. So Before we get into CO2, here is an abbreviated schematic of a supermarket rack, a multiplex DX rack. So DX, direct expansion. We're expanding the refrigerant. So just kind of going around the loop here, I'm going to start up here at the condensers. So you've got, coming out of the condensers, you've got liquid refrigerant. And that liquid refrigerant is going through a liquid header and then feeding all of the store cases. So it goes through the line to the expansion device, and that will expand the liquid from liquid to saturated. So when it goes into the coil, it's a liquid and a vapor mix. When it comes out of the coil, it is completely vaporized, it's superheated, and that's what goes back to the compressors. The compressors compress vapor, they don't compress liquid. Hard to compress that stuff. So going through the compressor, we have an increase in pressure and temperature. That ultimately goes through this network up here and gets back to our condenser, which condenses it back down to a liquid. So very quick summary of that system. But the thing that's worth noting is it is expanding refrigerant in the cases. And in this case, yeah, well, anyway, I just got a series of cases here. I'll just share that on this system, we have mechanical expansion valves depicted. We also have electric expansion valves depicted. And then we have mechanical EPRs and electric or EEPRs. So we can do all of that. Obviously, whenever there's an electric component, you're going to have some sort of a control. So this is showing one of our Kelvin platform controllers doing some of the work there on that. And there's other things going on here. There's subcoolers and there's heat reclaim. But, okay, so that's a baseline. That's what it looks like for a conventional HFC system. If we simplified it and brought it down to just its basic components, there's really 4 of them. And that would be the condenser and evaporator, so 2 coils, the compressor, and the expansion device. Every expansion system has to have that. The expansion device, that could be, there's multiple things that could be. That could be it could be a mechanical valve, it could be an electric valve, it could be a solenoid. And we'll talk a little bit more about all those and how they apply to CO2 shortly. So those are the 4 basic components that have to be there. And what I want to do now is I want to talk about where those components land in an energy, basically looking at the energy of that system. And so what I've got here is I've got what's called a pressure enthalpy diagram. Probably a lot of you guys know what that's about, but just in case, I'm going to go over it just briefly. And then superimpose on that pressure enthalpy diagram, I have this trapezoid, which is actually representing the vapor compression cycle for our refrigeration. So, but just to explain this, the horizontal axis, basically as I move more to the right, that's a higher enthalpy situation. And for our purposes, let's just say enthalpy is internal energy, the internal energy of the refrigerant. So the further right I go, the more energy I have in the refrigerant. And the further up I go, the higher the pressure is. So it so happens that with fluids, with refrigerants, with water, with CO2, there is there's a range on this pressure enthalpy diagram wherein the fluid exists as, well, I say fluid, it's a liquid and a vapor. And that's what we call saturation. So this dome right here, this is what we call the saturation dome. And underneath that saturation dome, there is it's saturated. It's liquid and vapor. The further to the right I go, the more energy I have. That means there's going to be more vapor, less fluid. As a matter of fact, if I go all the way across, like let's say that I take this line right here and I go straight across, as I'm moving to the right, I'm getting more and more vapor, less and less fluid, until finally I get to this point here, which is the dew point, and that's where, to the right of that, there is no more liquid. It's only vapor. It's superheated, it's above saturation, and so everything to the right of this dome is vapor. Everything to the left of this dome, if I go further to the left, I get more and more liquid until I reach the line here, and after that, everything below this is subcooled. Everything to the left of the dome is liquid. I don't have a bottle of water, but I usually shake a bottle of water around just to show people what liquid looks like, in case they didn't know. So, okay, so that's what's going on. Now, this trapezoid, the slope here, this angled on the right side, this is the compression phase of the cycle. And so basically what happens is we take the refrigerant when it comes out of the coil, the evaporator coil, and we compress it up to a higher pressure. So we're moving up in pressure and we're at the same time increasing in energy, internal energy, so an increase in enthalpy. When we come out of the compressor, then we enter the condenser, and the condenser, the first little bit of it, as it is condensing the refrigerant, it's actually de-superheating. So it's taking away the superheat until it gets into the saturation dome, and at that point, it's just cooling. It's condensing. It's condensing and removing latent heat, and it actually goes a little bit over the edge as it's condensing so that it gets into a full liquid state. If it stopped condensing right here, then we wouldn't have the liquid that we need to feed the expansion valves. So it goes all the way over till it's completely liquid, subcooled even, and then what we do is we drop it through that expansion valve, and that expands it so it goes from high pressure to low pressure. It goes from a tight liquid line into a big evaporator coil, and that expansion drops the pressure down, and that's where the cool happens. So when we get into, when we drop back into the vapor dome or the saturation dome, then what we do is we go through the evaporator, and we have that latent heat transfer where it's picking up the heat, the ambient air is being moved across the coil, absorbing heat until it gets right back to the start and goes back around the system again. Okay, that's a lot of, I just said a lot there, and I'm just going to keep moving. I don't know if that all made sense, but here are those components in the system superimposed now onto that trapezoid, so it's depicting exactly what's going on at those various stages. The thing to note is that the compression is always taking place in the superheated or the vapor side. Remember, all of this over here is vapor. The condensing and the evaporating are all taking place underneath the saturation dome. And there's a little bit of liquid in the system between the condenser and the expansion valve. Okay, so the vapor compression refrigeration cycle is the far and away most used means of refrigerating or cooling that we have. And it all comes down to those four basic components. So understand that at the core, because actually, although we're gonna step a little bit outside of that realm with transcritical, nevertheless, most of what we're doing, even with CO2, it's still the same thing. It's the exact same thing. So, but before we get into that, I'm going to take a step back, and we're going to talk about not expansion, but we're going to talk about a glycol system here, a secondary glycol system. Basically, what we're doing is we're moving a glycol water solution around the supermarket, around the store, and that's what's going into the cases, and the warm air is going across that cold coil with glycol in it, and that's where the heat transfer is taking place. So the beauty of this is that if this is your store, and of course this is very abbreviated, but if this was your store, the store has got nothing but water and glycol mix running through the lines. So you've got a very low refrigerant charge, which from a sustainability, from an environmental standpoint, that's a good thing. All of the HFC, all of the synthetic refrigerant is back at the chiller, and basically what it's doing is it's cooling this braze plate heat exchanger, or what we call a cascade evaporator condenser. It's an evaporator on the one side, and it's a condenser on the other side. Although again, it's really not. It's not condensing because it's already liquid anyway. So this is something that we started doing a number of years ago. We've got some stores out there with this in it. This kind of a setup, and nobody's doing this. I mean, I don't think anybody's doing this right now. And the reason why is because although it eliminated a lot of refrigerant, it required a lot of energy to move that glycol around to keep it cold enough and to get it to the cases efficiently. It's just a lot of pump energy, and it ended up just being prohibitive, cost and energy prohibitive, really energy prohibitive, I think. Looked good on paper, but it didn't work out well. There's probably some things that could be done to improve this, but right now everything's moving away from this. But I did want to bring it up because the concept of a secondary coolant, the concept of having something flowing through the store other than a synthetic refrigerant, that's what we want to do if we can. So, and that's where we start talking about CO2. So CO2, also refrigerant R744, we can utilize that in at least 3 different ways. We can use it in essentially a secondary fluid type of a operation, which is liquid overfeed. We can use it in its subcritical condition, and we can also use it in a transcritical condition as well. So we're going to go over all of those. So in these first 2, as it shows here, these first 2, liquid overfeed and subcritical, these still require an HFC chiller, if you will, to do the primary cooling of the CO2 before that gets fed out to the cases. So we'll get into that. And on the right-hand side here, I just wanted to show that, you know, it's not all rainbows and butterflies. There's some issues with CO2. There's 2 issues. One is the high pressure. So on a low temp rack or low temp case, negative 20 degrees, this is basically a pressure temperature card right here. So negative 20 degrees Fahrenheit, that's equivalent to 200 PSI. And on a medium temp at 20 degrees, you're looking at almost 400 or around 400 PSI. So those are pretty high pressures. And then the other challenge or disadvantage with CO2 is that it has a very low critical point. What's the critical point? The critical point, I wished I had a slide in here, but it doesn't show a slide of, there's something called the triple point. Does anybody know what the triple point is? 68 pounds. What conceptually is the triple point of a fluid?
Or it won't condense anymore? The conversion from liquid to dry ice.
The triple point is where it's that point between where you would have a solid or a liquid or a vapor. So depending on the pressure that you're at, and at a certain pressure and temperature, you'll have a point where you step over that line in one direction or another, one of 3 directions, you're either going to become a vapor or a liquid or a solid. It's pretty interesting. And that's where you get in, it's like, well, what is that? So sublimation, that's where something goes from a solid directly to a vapor. It doesn't become a liquid. And so that's the chart, the image that I wish I had shown, that shows the triple point and the critical point. The critical point is another weird thing because basically the critical point is along the line that's the crossover between liquid and vapor. But if you follow that line far enough, with increasing pressure and temperature, you'll get to a point where that line disappears. And it's called the critical point. And after that point, there is no boundary between liquid and vapor, and there is no liquid and vapor. There's only a supercritical fluid. So although I don't have that image, I do nevertheless have this image. And I just realized, oh, I see, I didn't hide that. I didn't hide that up there. But you can't read that. You'll read it in a second. But this is, again, that pressure enthalpy diagram, and this is showing the critical point from another perspective, and that is pressure versus enthalpy. So what happens is we've got that saturation dome or that vapor dome again, right? Well, what our trapezoid down here is showing is typically how we run our system. This is where subcritical operate. This is where a normal DX operates. And this is also where subcritical operates. If you take CO2 and you expand it and you increase its enthalpy, you blow hot it, you pull some of the heat load out of a building, then what's going to happen? That CO2 is going to leave a condition of saturation and it's going to become superheated. And then you take that CO2 and you compress it, and then you run it through your condenser, and it'll go from a superheated state to a saturated state. And as you move along this line, you'll become more and more liquid until you get completely liquid CO2, expand it, and just keep running around. This is just normal. This is just exactly what we've always done. This is direct expansion, but with CO2. The problem is that the critical point of CO2 is like around 87.9 degrees Fahrenheit, and that's right up here. That's the top of that saturation dome. So if this is over here, left-hand side, that's all liquid, and over here, this is all vapor. Well, what happens up here, right? Well, I'll tell you what happens up there. That's where transcritical refrigeration happens. So we have to add a whole nother trapezoid onto our slide, because what happens is that if the ambient conditions are above 87.9, then we don't have liquid CO2. So we've got a little bit of a problem there. So what we're going to do, and we're going to get into that a little bit more later, but we're going to show you how we can handle the CO2 up there in that transcritical realm. I will say that it's interesting. If you're north of this vapor dome, you're in what's called you're a supercritical fluid. Supercritical. It's above. Super is above. So superheat is above. It's the temperature above saturation. Superheat is the temperature above saturation. It's that delta above. Supercritical would be the temperature above the critical point. So if my CO2 was up here, somewhere up here, somewhere over here, it's not a liquid, it's not a vapor, it's what's called a supercritical fluid, and it's like weird sci-fi stuff. So get on YouTube, look up supercritical CO2, and there's some pretty cool little demonstrations and experiments and stuff that people do with that. It's kind of interesting, and how things will flash to dry ice and stuff like that, depending on the temperature. Okay, so we'll talk more about that in a minute, but so like I said, there's some drawbacks to CO2, and one of them is that in order to deal with that supercritical fluid, we have to go into that very high pressure range, and so we're going to have high pressure in our system. And if the system shuts off and it's allowed to just warm up to ambient, then it's going to go supercritical, and it's going to be very high pressure. So there's additional measures that have to be taken into consideration and deployed. Like in this case, what I'm showing here is a check valve being routed around an isolation valve. And that's so that the components downstream of that, if the system's warming up, it's allowed to vent the refrigerant, the CO2, out beyond that or around that, that isolation valve. Otherwise, something's going to pop. High pressure. I was going to say something else about that, but, well, I'll keep moving here. So that's a good intro to our ball valve. Sporlan makes a ball valve that has a built-in relief valve. It's a check valve. So you'll see these on the system. There's a little A right there. You just need to make sure that you point the A towards, like in this case, point it toward your coil, because there's a lot of refrigerant in there that we want to be able to get out of there if it needs to. Okay, so we talked about glycol. Now, this is secondary, not glycol, secondary CO2, otherwise known as a liquid overfeed secondary system. And it looks kind of similar to the glycol loop. They put an extra case in here for good measure. But here again, we have basically a chiller up here on the top left, and that's what's going to do the primary cooling. And then the CO2 is being circulated in the system to take that cooling to the cases out on the floor. So this is using a pump. It's basically pumping liquid CO2 around the system. And then check this out. It's just using a solenoid valve, because with an overfeed system, you've got more liquid going to that case than what you really need. Now there is a phase change in this coil, but because it's going to be saturated all the way through. I'm not going to superheat it at all. So all I need to do is put a set point on these and use a solenoid valve to just open and close. So I'm not metering refrigerant with an expansion device. I'm just open, close the solenoid valves. Coming out of the coil, I've shown the ball valve with the check valve in parallel. I didn't show the Sporlan integral valve, but nevertheless, that's that there. Return suction header goes back to it's being called a receiver. It's a it's a vessel. Yeah, thank you. That's the right word. It's a vessel. It's not really a receiver in the traditional sense, but from that vessel, again, we're just going to pull the liquid off. We don't want to cavitate in the pump, and then we circle it right back around again, and then the CO2 is being cycled through that heat exchanger to bring that temperature down. So that's how we do it this is beautiful, because now we've just got kind of like the glycol, we've just got the HFC on the chiller plant, and then through the store, we've got nothing but CO2. And by the way, I forgot to mention the whole point of CO2, which I think you guys know, but CO2 is a very low GWP. It's got a GWP of 1 versus 404 that's got a GWP north of 4,000, I believe. There was a question?
So there's actually no change in state with the CO2. It's just pumping straight liquid.
Is that right? So through that, you're telling me that, oh, you're asking me?
Yeah, so what's the green? When you show the blue and the green, is the green different? Is that a higher pressure or still liquid? Or is it a mix?
The blue has been superheated.
I'm sorry, say that again.
The blue has been superheated. Basically, now going through the heat exchanger, now make it cold again, the CO2. So you release all the heat. All the green is basically heated superheat.
My understanding is it's in a normal coil. What do you have in the coil? What's the condition of the refrigerant in the coil?
Saturation.
All the way?
No, maybe halfway.
It's mostly saturated, but at the very end of it, it's superheated, right?
Yeah.
So in this case, this is all saturated, or I should say it's basic, because look at this is not, again, it's not an expansion device, so it's showing green here. That's probably a little bit confusing, but basically when that opens, you're going to have liquid just feed straight in, just straight liquid. But as it's picking up, as it's doing the heat transfer and that CO2 is picking up BTUs, it's going to move into a saturated condition. But it's never going to go above saturation. It's going to go back as a saturated, and then just separate out the saturated liquid from the saturated vapor. That's my understanding of it.
And this one's just a DX subcritical secondary CO2. So all we're doing is using DX on the left, and you're pulling the vapor through the subcooler on that fan frame. So as you pull that gas from that receiver, you turn it into liquid at the bottom, liquid sits at the bottom.
Yeah.
You just recirculate the
Yeah.
pump to the cases.
Yeah.
That actually, I don't like it saying liquid solenoid, it's actually acting as a pulse valve. So that valve is clicking, click, 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 maintaining superheat, and that's how you're getting that expansion at that evaporator.
It's
As
yeah.
you would like in a CO2 scenario, but
If it's sized properly, I don't think that if the lines are sized properly, I don't think this is acting like a pulse valve. It is on off,
Yeah.
but we have a pulse valve and that's clicking. So this is you're
What you're gonna have is like you have to define your overfeed rate. So if it's like for this scenario, it might be 2 to 1 overfeed. So
Okay.
you're sending 2 units of liquid CO2 in and getting 1 out. So like you're gonna have an overfeed rate. That's similar to ammonia. You might use like 3 to 1.
Yeah,
Yeah.
a research, yeah, but that's because you have a compressor pumping, or you have a compressor sucking, so you need to have that vapor, so you'll have like about a 3 to 1 ratio on the recirculating. So your evaporators, when you have wet suction, when it's coming back, you'll have 3 parts liquid and 1 part vapor.
Actually, the solenoid always stays on because if you shut off, actually it's getting even colder because when it starts boiling off, it will make it colder. So now actually you really drop the temperature.
yeah.
Faster.
Yeah.
As the CO2 return comes back, it's getting colder actually when you splat. It's just the opposite logic and normal as a refrigeration system we use.
Yeah, that's a good point. So I don't know how many of you guys have worked on one of these? Okay, yeah. Like I said, you guys have that experience. So, so this is the first step. So I got two more steps and a half step in the middle. Oh, I've got this question here. Why secondary CO2? Again, to reduce the total HFC charge in the system, it could be dropped by by 80% reduction. CO2 has a high heat transfer coefficient, so we can get a fast pull down with CO2. CO2 also has smaller pipe diameters, so it's pretty easy to run that stuff. It's less expensive to install. And it's a win over glycol, because the glycol, remember I said that the glycol, there's a pretty big energy hit to circulate glycol in the system. So CO2, not so much. Oh, okay, yeah, so worth noting that this is the solenoid valve that we deploy for these applications. So this is our XSP. It has a tight, it's the kind of its claim to fame is it's tight seating at low pressure differential, whereas the others not so much. So you'll probably see these out there. Ensure closures during defrost. Yeah, there you go. That's the solenoid for that application. So and that's not our pulse width valve, and it's not one of our standard solenoid valves that we would use for just a liquid shutoff or liquid line solenoid. Okay, so here's the next step. So we just looked at overfeed, secondary system. Now we're going to talk about subcritical cascade DX. This green, what is that color? This lower trapezoid, that's our subcritical CO2. But in order to get that CO2 into the subcritical range, we're using an HFC on the chiller plant, if you will. And then we're we're expanding, this is a true subcritical system where we're actually expanding the CO2, and we're taking liquid CO2 and we're expanding it, and we're taking it through saturation all the way to a superheated state, and then we're bringing it back around again. But in order to make that happen, we need the HFC chiller on the high side. So I'll show you what that looks like. But what I want to say before that is that this is not actually accurate, because this pressure enthalpy diagram is a CO2 pressure enthalpy diagram. And so what I've done is I've superimposed let's just say that's a, I don't know, 404 trapezoid on top of it. So that's not actually accurate. But for the purpose of diagrammatically showing you what's going on, that kind of communicates the point. So here's the cascade system. So as I said, there's still a chiller up here. So there's a brazed plate heat exchanger. We're metering refrigerant in it. We're expanding refrigerant into that exchanger, and that's your HFC. Now, in the last slide, I had a pump. In this slide, I don't have a pump. In this slide, I have compressors. So this is a receiver tank coming out of the heat exchanger, and we're pulling off the bottom, we're pulling the liquid out, and we're feeding the liquid to the cases. Those are going through an expansion device. In this case, I'm depicting a electric expansion device going into the evaporator, and then it is doing a full DX heat transfer and going back vapor to the compressors, because the compressors only compress vapor. So those compressors then bring it back up to temperature and pass it back through the heat exchanger, and the cycle continues on its way around. So this is going to be for low temp, mostly for low temp, because we need that compression to get that delta, to get that lower temperature that we're looking for. I don't know what else to tell you about that slide. Does anybody have any questions about that slide?
That's all CO2? Or no, you have
Yeah, go ahead.
Yeah,
Exchanger? A regular condenser?
What's the question?
All right, guys, listen up. Listen up. Let's bring it back in. I know you guys are gonna want to go over this some more. But the question was, why don't we use a regular condenser up here? Why are we using this brazed plate heat exchanger? The answer is that's just the tool to get the job done. We're passing two fluids across each other through that. A condenser, in the normal sense, is going to be basically the two fluids on a condenser is going to be air on the one hand and the refrigerant going through the condenser. So does that?
No, I'm just asking why. Why not use fan?
So I've seen on this one, like Walmart's will be retrofitting, they have a DX racks on the roof, and they might want to lower the charge, so they're using this as like a retrofit, like adding a CO2 loop for low temp, and they're just adding a brazed plate heat exchanger in between, and then maybe another 5 or 10 years later, they might get rid of the HFC rack.
Yeah, so the HFC rack, that's basically what this is, right? So you need that, essentially the chiller, to chill this brazed plate heat exchanger. The reason why we can't use a normal condenser, well, I'm going to get into that in the transcritical mode, but basically we're not
You're not dropping your discharge pressure low enough.
Yeah, that's right. You're not dropping it low enough to be able to work with it.
So the coil would have to be huge to.
No, it's thermodynamically impossible because of that critical point that we were talking about. And I'll get into that a little bit more when we get into the transcritical section. Because with transcritical, you are using on what's called the gas cooler, you're doing that. You're blowing fans across the coil, right? So it's like, oh, that looks like what I'm used to. But the interesting thing is that it's not actually doing what you're used to it doing. And that's why they don't call it a condenser, because you're not condensing. You're just cooling. And yeah, we're cooling in this case. So on the other side of this loop here, like these are cut off. But on the other side of this, there is a condenser.
Another refrigeration system.
It's another refrigeration system. It's a refrigeration system on top of a refrigeration system. There was a question back here?
Yeah, no, I was just gonna help him out. So you're looking at that flat plate heat exchanger up there. That's running your standard medium temperature. That's not running like 80 degrees. So when you're dumping that CO2 coming out of your discharge on your CO2 compressors, that's not as hot as your, normal discharge is.
Yeah, your
So you're
discharge has to be
dropping that
around 400 pounds.
Yeah, and then
For
you're
low
gonna
temp.
drop it down to like 200 in that flat plate heat exchanger. So it's not as high pressure as what you're thinking, and you're not
Right.
condensing it necessarily. I mean, you're condensing it, but it's,
Yeah, that's good.
You can't do the same with a.
No, I get all that.
Yeah.
What I'm saying, as an engineering end, why
So
are we doing that?
yeah, you can't use a gas cooler to do that.
Stay tuned. Let's keep moving, and then we'll get into the transcritical section, and hopefully that'll shed a little bit more light. So, okay, so that's a subcritical cascade, and to assist with that, we do have expansion valves. This is the SER, and actually I've got one of these right here. This is a SER, what is this? A, and it's an SERA. It's got a inline strainer built onto it, so you can unscrew that strainer and clean it out if you need to. All the advantages that you normally get with a stepper motor valve. You got the high resolution for precise control. You're going to have to have a controller. There's some electronic controllers on here. We can use the EEVs to control discharge air. We can use it to control superheat. There's some other things we can do with the controllers, and I'm going to leave it at that. So that's basically just showing you. This is an electric expansion valve, and this also shows an electric EPR valve on the back end to control the suction pressure or the evaporator pressure. So that could be used for like a dual case application. This is the liquid line solenoid valve. This is just our standard. It's not our standard. It's our dash HP solenoid valves. So our dash HP valves, those are high pressure. We originally came out with those for 410, but for the pressures that we're talking about in subcritical CO2, those work all day long. So for the liquid line solenoid valve, you've got, our standard line of solenoid valves. Now, I'm showing here, I didn't talk about this yet, I'm showing a solenoid valve in series with an electric expansion valve. And that's because if you have the system shut off, if you lose power, let's say, the stepper motor valve will stop wherever it is. And so if it's at 20% open, when it turns off, it's going to stay at 20% open. If it's at 70% open, when it turns off, it's going to stay at 70% open. But we really want to close the line so we don't have refrigerant continuing to move into the evaporator, and that's what the liquid line solenoid valve does. So that's where just use our regular HP solenoids, and you can get that job done. Now, this next slide is showing our pulse width valve, and we call it an SPW, Sporlan pulse width, and that will kill two birds with one stone because this is actually modulating the valve to expand the refrigerant, so it's our expansion device, and at the same time, it's also our liquid line solenoid because if we do lose power, that valve will go closed and you'll stop the refrigerant flow. So it's killing two birds with one stone. It's actually killing like over 3,000 birds with one stone because that single valve there replaces about north of 3,000 SKUs, Sporlan specific item numbers that we have because it's so universal. It's got 8 different interchangeable ports or cartridges that you can put into it, depending on what your tonnage is. The SPW8 is I think it's around 12 tons. I don't know exactly what the tonnage is for each of those SPW1, SPW2, SPW3, SPW4, but suffice it to say, we've got a broad range that we can cover. This is good for CO2, it's good for HFCs. Yeah, and so that's the Sporlan pulse width valve. Probably some of you guys have worked with those. They're definitely out there. Yeah.
Do you guys have issues with those boards dropping out and frying those? So if that were to fail, do you have any issues with that particular controller frying those, getting fried based off that valve failing?
No. I've not been exposed to anything of that sort. Has anybody experienced a board failure due to a valve failure? Is that
On 6, 7, 8.
Yeah? Okay? So is it shorting out in the valve, and then that's causing the board to somehow short?
So the valve shorts out, and the setup that we have, it's refrigeration, but it goes back to a Dixel, and it shorts out the Dixel, then it kills the comm loop.
Exactly. Drops out and it'll hit all the way back to the pin board.
And it's all, the
Drop
root
the
cause
bolster
is
down while
something
you're
that
in.
happens inside the valve.
So wait, okay, I see what you're saying. You're saying that the Sporlan valve shorts, and it takes out the Dixel.
The
Which
Dixel,
in
this
turn
is 7,
takes out the entire comm loop.
But it's not our controller. So you're talking about other controllers.
I'm asking about your controller, yeah. We're
So-
talking about Dixels, 6, 7, 8.
So
When they run them on that type of valve, because you're a stepper valve.
yeah. So
Because on CO2 applications, the 6, 7, 9s are the pulse valves. There's not a lot of issues on those. They don't drop out. It's only on that type of valve, that 6, 7, 8. There's no issues on the 6, 7, 9 dropping out networks,
yeah.
frying, and like you said, they fail at whatever percentage they're at. So you get there, it's fully iced up or whatever. You may be washing out the rack, but yeah, those particular valves.
Yeah,
Swap out.
I'm gonna make a statement, and then I'll let the crowd react. I think it's a controller issue.
That's why I was asking about your controller.
And the reason I say that is because if the valve shorts out, you want to design your controller so that it's not gonna cause the controller to kill that board and then kill the whole comm line, right? So has anybody experienced a complete comm loss with the S3Cs?
I don't see those, that's why I was asking.
Okay.
But this will drop, you assume, yeah, it's just one board, but it'll drop out the whole network.
It'll drop, right, exactly. So, yeah.
Disconnect that one, you'll get the network back. But if you unplug
I've-
the valve, you plug in the network, you're good.
Yeah.
The valve internally just drags down the whole network.
Yeah, I have heard of that, and I don't remember if it was a Dixel or if it was I think it was an Emerson board. I don't recall, but as I'm thinking about it, I don't know how you could design
You have to have a comm pass through or something.
I don't know how you could design the valve to have some kind of a safety mechanism so that if the valve fails, it doesn't trickle back to the. I don't know. That would be an interesting thing to look at, but
The valve frying the controller? Is that what it's doing?
yeah.
It's frying.
Mm-hmm.
Or is the controller frying the valve?
Well, the valve is internally shorting out, as I understand it. And so then you've got that voltage going back to the controller in a way that the controller wasn't anticipating, and it shorts it out, apparently, fries it. So, okay, so that's a good thing to look at and think about. This now, what I'm depicting here is a combination of those two things that I have already shown you. So on the top end here, these are going to be basically our medium temp. And so these don't require compression. These just have that pump that's circulating the liquid, and then it's taking that liquid back out, and it's saturated and separating out the liquid and just circulating that around. So that's our secondary CO2. But down here on the bottom is our low temp, and these are requiring compression to get that additional drop. And so basically, I've got the same liquid, it's common liquid line, common liquid header, And these require the actual expansion valves. And then when it comes out of suction, it goes back into compression and compresses it back up and puts it back into the receiver there. So that's just a combination. But it still requires the HFC chiller up here. So it's a beautiful thing because the store does not have all that high GWP refrigerant flowing around. I'll call it the evil refrigerant. Okay. Fun. Now, yeah, question, Ruben.
Why not use a small ammonia package?
You could. You could on the top, right?
There's 5 of them installed in the United States.
That would have ammonia on top of the CO2?
Over here, so
Albertsons and Fullerton.
Albertson's right down the road here. So yeah, take this and turn this into an ammonia chiller. Yeah, it'll work. It'll work. HFC, ammonia. Now, if it's ammonia, obviously it's natural refrigerant. So boom, you're totally clean there. But there's something else that we can do without having the ammonia that, I don't know, a lot of stores probably don't want to have ammonia in them. I don't know.
You get a leak, I mean, you got to vacuum it down, everybody's gonna die.
But it's only in the rack. It's only in the rack room, right?
Still in the case?
No, not the money, the whole money.
it's all on the roof. It has to be under a chart.
You got that big old orange flag to tell you which direction to avoid.
That's only on the industrial stuff.
Lights do ammonia. Yeah.
Okay. So instead of using an HFC up here, and instead of using ammonia up here, what if we use CO2 up there? Right? Let's just use CO2. We've got CO2 in the cases. Why don't we have CO2 in the rack? And so that's where the transcritical CO2 comes in.
Yeah, sulfur sucks to the.
All right.
You got 25 minutes.
I got 25 minutes, okay. So basically what happens is that we've got that, it's kind of hard to see, but this is where, this is our trapezoid for our CO2, subcritical CO2. And it's subcritical because it's below the top of the vapor dome. So it's not critical, it's subcritical. But then what happens is that we have to compress the CO2 up to a high enough pressure so that we can then what we do is we compress it, and then we run it through a gas cooler, and then we expand the CO2, and when we expand the CO2, we drop back under the vapor dome, or the pressure dome. Vapor dome, that sounds like a Tina Turner, what was that movie? Thunderdome. We got to get back under the Thunderdome here. So, okay, so here's the way we do that. This is the transcritical CO2 system. I'm going to break this down into little bite sizes. A lot of this is very much the same. So let's start over here on the right-hand side. That's our normal subcritical DX. That's what we've already seen. Nothing new here. We've got liquid that's being expanded into the coil, and then it's going back to the suction header. There's nothing new there. I don't think there's anything new there. So, been there, done that, good. Let's go to the next one. Coming out of those cases, we go back to compression. And this is parallel compression, and so this is what is referred to a lot of times as a booster. So what we're doing is we're taking the low temp cases and we're boosting, we're taking that CO2 up to the medium temp, and then we're feeding that into the medium temp compressors, and then we're pumping that up to the high temp. We're taking that up to the high pressure that we are going to then feed into the gas cooler. So that should be pretty straightforward. It's just parallel compression. This is the part that's new. This is the gas cooler. So feeding in from the left-hand side, these red lines got cut off, but that's just coming from the compressors, and it's got an option. If we want to get some heat reclaim, it goes through a heat reclaim loop, and that's being controlled by a modulating valve, or we can run it straight into the gas cooler, or a little bit of each. And that's our gas cooler. That's got our fans on it. It's blowing air. It's on the roof. And yeah, that's what's going on. It's not a condenser, because if it was a condenser, it would be condensing something inside of it. And it's not condensing anything inside of it. It's just cooling it down. So that's why we call it a cooler. That is being controlled by the gas cooler valve. So that gas cooler valve is controlling the pressure in that. And what's happening is there's a huge pressure drop that's going through that valve. So that's kind of like our expansion device. That's expanding into the flash tank, which is also called a vapor liquid separator. So from the flash tank, we take that liquid and we just feed that liquid to our cases, just like normal. Bada boom, bada bing. But we've got to regulate the pressure of this tank, and we've got to do something with all that gas. And so what we can do with that gas is we can bleed that gas off, controlling it through the flash gas bypass valve to take that back around, dump it back into the medium temp. Well, actually, yeah, there's a few things that we can do, but we're going to ultimately loop that back around and just continue cooling it and putting it back in the flash tank. And so it's looping around.
So I've only seen iPros and Danfoss controlling those valves. What control are you guys using to control those? I think they're normal.
We can integrate with those or microthermo. That's it. It's one of those guys, basically. To my knowledge, I don't know who else. What else is controlling these valves? Anybody have any? You said Danfoss,
And iPros.
iPros, microthermo.
Microthermo, yes.
Oh, okay. I thought
Corel.
those were your controllers right there.
The E3. I don't know if that. We'll say it again.
I thought those were your controllers right there, yeah.
Yeah, this is not a very good. Because that's actually our Kelvin 2 platform, and that doesn't. We don't have one that control. Well, I guess I would have to find out if we can use our pressure controller, because we have a pressure controller in the Kelvin platform. I don't know if we could use that for this application, but typically that's not what I've, to my knowledge, that's not what's being used at all. So, okay, yeah, this is just showing what I just showed you. There's the gas cooler valve, there's the flash gas bypass valve, and there's what they look like in real life. So it's got our standard 42 millimeter digital linear actuator on top, and then it's got the stainless steel body for the high pressure. We've got these in a number of different sizes, and we're actually working on generating some new, some smaller sizes of these. I've been told that the gas cooler valve for a small application can also be used as a flash gas bypass valve, and I've also been told that an SDR can be used in the place of a flash gas bypass valve. So going back to this pressure enthalpy diagram, we're having the compressors. So you can see there's superimposed one on top of the other. We're going to have compression, and then we're going to have more compression. We're going to have that booster compression going on over here. Then we go through the gas cooler, where we're only sensibly cooling. There's no latent heat transfer. We're not changing any phase. So we're just sensibly cooling the supercritical fluid, and then we jump through that we jump through the gas cooler valve, and that causes a huge pressure drop, which brings us back underneath the saturation dome. And at this point here on our graph, we either take the liquid, we take it to the left and we go back to liquid to use in our cases, or we take the gas and we pull that off and we bring that back around through the gas cooler. So there again, that's the whole enchilada right there.
Green or red? The green enchilada? Red enchilada?
There's some other things you probably have already heard about if you go to some of the other presentations about what we can do with that flash gas to be more efficient. But man, what time is it? What have I got?
You got 9:45.
I got 15, 20 minutes about? Okay. So, yeah, there's a lot of changes. Expect more changes. Alternative refrigerants, including CO2. It's here, it's now. And now I want to talk about the S3C, just to give a kind of a high overview of this product. A lot of you guys have already worked on these. We've got, I mean, I don't call on case manufacturers. I had no idea how many of these we had sold, but we've got many tens of thousands of these out in the field right now. And so I call on a lot of the wholesalers, and I'm looking forward to when they start selling these. So that'll be good. S3, that's safety, service, and security. So that's where the S3 comes from. Safety is food safety. But what we did is we went to the large supermarkets, and we said, what do you guys want? And this is what they wanted. They wanted to make sure the food was going to be safe. They needed a better solution than what they had. They wanted to also have serviceability. So that basically is in the form of the diagnostics, which you can access through the digital display. But if you really want to get things done, you need to get the TechCheck app. So you go to the App Store and download the TechCheck app, and that'll give you a way to get into this. Now, you have to register to get access to that app, but yeah, question?
So if the network fails, it'll act as a standalone?
Yeah, exactly. So finally, the last one is security. They wanted security. So if the network goes down, these are completely standalone. So they're open protocol, so they can communicate with the E3s or the microthermos or whatever, but they're also completely standalone. So when all else fails, it just keeps on doing its thing. It's your insurance policy. Okay, so yeah, as I just described, they wanted those three things. The other thing that they wanted is they wanted an accelerated delivery, accelerated commissioning of the stores. They wanted to be able to drop a case in and within a day drop a store in and within a day have everything set up and running. And so the way that works is every single case has its own address, and every single case is theoretically preset from the factory with all of the set points that are appropriate for that particular case and situated on the lineup within the store. It's all supposed to be set up because they wanted to have it next day, basically plug and play. So I don't know how often that happens, but it's at least it's at least an improvement, hopefully, not at Walmart. So, and a lot of that is the case manufacturer. You know, we're looking to them everybody's looking at them to make sure that they get it set up right, so that when you drop it into the store, it's ready to go. But I'm sure that's not an easy task with all the complexity of a store system. This image here is just showing that somewhere on this case, you're going to have to figure out a place to put your controller. If you got a valve module, a power supply, and the digital display. These are not always in the most convenient places. So wherever these go, you need to make sure that they're underneath the umbrella because they're not IP rated. So if you hose them down, they are going to fry, most likely. So they're yeah, they're not, and they shouldn't be mounted inside of the refrigerated space. So outside of the refrigerated space. We can, with a case controller and a display module, every case controller needs a display module, we can control the superheat on this coil. We can also control the discharge air coming off of that coil. And we would do that with the solenoid valve. It says optional, but it's really necessary. You really want to have that on there. just to be able to shut off refrigerant flow. We can have 2 coils if we use an additional valve module. So we have the main case controller, we have a valve module, and then we always have to have that display module. So in this case, the valve module will drive the second stepper motor, and I got 1 liquid line solenoid feeding both of those.
So is 2 the max you could have for 1 controller?
For 1 case controller, I can have one metering valve. Yeah. If I want to have if I got a second coil, I'm going to need another valve module.
How many of those can you add up to that?
2. I can put 2 valve modules on.
Okay, so total of 3.
So I think 3.
Run out of room.
S3C, it would take three electronic EXVs, right?
It can control 3 EXVs, yes.
Total you will have 4 so far.
Wait, let me back up. This main controller,
Only one.
only 1, yeah.
The next module, expansion board, you can have up to 3, controlling 3.
The next board, I believe, will control 2 stepper motor valves.
Only 2?
So yeah, just 2, no more than 2. So that would give us 1, 2, 3.
So that's what you could have.
Yeah.
But it's still controlling the one, that would be the solenoid still.
Right. So here's another shot, and this is just showing again basically what we just talked about. You can do 3 stepper motors with just a controller and a valve module. And like I said, we can control discharge air on each one of those coils. Now in this case, the liquid line solenoid is going to be hitting all those at once. So it's going to look at the main valve. Actually, let me back up. It's using an aggregated discharge air to make the call as to how it's going to modulate that valve. So it's basically doing an average. But we can also use an EPR or an EEPR, a dedicated pressure regulator, to control our pressure on that coil. And the way we would do that is, in this case, the stepper motor is going to be controlled with the main control module, and then the EEPR is going to be controlled with the valve module. But you need to make sure there's some dip switches on the left side of that board, and you got to flick the first dip switch to make sure that it's down, so that that tells it. And we've got more on the specific setup of this, but that will tell it that, hey, this valve module is controlling an EEPR, not an EXV or an EEV.
And with that one, you would only have 1 and 1, right? On that.
Yeah, 1 and 1. So, yeah, we've already talked about the main controller, valve module, the display. This can control, well, there's not much to say here. It's all can integrate all the way back to the BAS system. So, I guess what I would share is that there's a number of inputs and there's a number of outputs on this board. So the inputs are going to be temperature inputs, pressure inputs, switches for like the door switch, or motion detection, or occupancy detection.
So is this gonna be the same system for the CO2 racks?
Yes.
Okay.
CO2 cases. CO2 cases, yes. Exactly.
So you
Yep.
can use the same board, same setup, same.
Yep.
All right.
Yep. We also can control the defrost with these, control the lights. So the lights are on a timer to make sure that they are on and off at the right times. Fans, anti-sweats. So that's all being controlled with this if the customer wants them to be. They all need a power supply. And as I said, they all come back to the BAS controller. Now,
Can you go back to, what was the power supply? Yeah.
24-volt DC output, 2.5 amp.
Do you have
60, it's a 60.
Do you have spare outputs on the main board? Or you just,
Spare outputs for,
if the fans were to fail?
no.
No.
It's like a
And you're
case
saying-
control.
But it is fused. The board is, it's all fused. So, I don't know if I can.
You're gonna have your vacuum pump?
Well, at any rate, we can do it later, but these are fused.
He said, you don't give me a vacuum pump, you have to change the fuse.
Yeah, so they're in the module right here, you can see a fuse right there, so you can take a look at that. But the main board as well pops right off of there, and you can change the fuses out. This is showing how, well, each controller is going to be given its place it's basically, you're going to identify what case, in which lineup, coming from which rack, and that is all going to be integrated so that it can basically go back to your BAS. We use Modbus and BACnet for protocol, and it can all be accessed remotely. So, the store of the it's up to date, current technology with what's going on out there, so we can remotely access it. We can have 38 of these in a loop, and we can have, I think, up to 8 cases in a lineup, for whatever that's worth. This is also showing the gateways. So the gateway can be, there's a couple different ways you could put that gateway, but the gateway is basically a cellular gateway or a router that will allow us, or tech support, actually all the tech support for this product is routed through microthermo. So that's who you're actually talking to. So if somebody sounds French when you when you call them up, that's why. And this will give them the ability to get into the system and do some administrative adjustments depending on the customer, if to the extent the customer is allowed those changes to be made, and they'll be able to walk you through stuff. So
You guys have updated your app, and all the techs now have access to like update all kinds of stuff, so that's really nice right now.
yeah, nice. For which store?
This is a Walmart in Belém, Mexico.
Okay. So yeah, there's a limit to what access you're granted based on, Walmart has their own, what they consider to be acceptable for what you can get to. You can access a lot of things with a remote display, but you've got to have the administrator password to access some of the other things.
What is that? Yeah, you have to call.
Yeah, it changes. It's different, and even the well, anyway, there's a tech password and there's an administrator password. And then, but again, with the TechCheck, you get that. You download it off of the App Store. I don't even know if you have to take the test to get access. I think if you just request access, you'll get access. But they'll know who you are now. So that way, if you do some things, I think they can track you that way. You can go in and with this or with a TechCheck, you can temporarily change some of the settings so that you can do some diagnostic work. And I don't have a deep dive on the TechCheck app, but I'm going to jump through these. The gateways, there's a couple different gateways that we're selling. They both work. There was a supply issue getting some of those gateways. Again, that allows our tech support to connect. I actually didn't think about this earlier, but I learned that some stores will have multiple gateways in them, and sometimes people have actually borrowed a gateway from one location to take to another location because that other location didn't have one. So that'll allow you to get connected. Again, a lot of opportunities for working with this through the display and the TechCheck app. And this does all these different things. I think we talked about all those. We touched on all those. Have you guys used Virtual Engineer? Changing the subject. If you go to our website, if you go to Sporlan.com, we have Virtual Engineer. Just go to Sporlan.com or scan that code, and that's a tool that'll allow you to select our products for whatever your application is. You just enter the parameters for that. So that's a good resource. This is just showing how to get there. Get on our website, click on Virtual Engineer. It'll take you in. You can watch a video to get a little more understanding of how to do it. And we also have all of our literature. There's some holes in our literature, but we do have literature, and there is a 147-page document on our website for the S3C, so you can get more information there. And finally, definitely get signed up for Chill Skills, Chili News. So Chili News is going to be a periodical release of some of the different things that we've got going on. And if you go to our website, you can go to Chill Skills, and you can get a lot of training on a lot of our products. It's a really good resource. I highly recommend it. Or you can just Google it. Not Google it, you can YouTube it, and you can get in there as well. But Chill Skills has got a lot going on. This is Sporlan tech support. Again, S3C is all going to be handled through Microthermo. So you could always call here, and they'll give you that information if you need to get some tech support.